All right, so good morning. Happy Friday. It's Friday. And then next week is a short week for you, and then after that I think we have 2 more weeks, and then Santa Claus pays us a visit. Yesterday we learned about what mechanical energy is. Mechanical energy is the sum of kinetic and potential energy in a system. And we talked a lot about pendulums, but it could also be any situation where you have mechanical energy being conserved. What that means if mechanical energy is conserved is that there's no work being done. In other words, there's no outside forces, and we call that an isolated system. And in addition, there are no forces of friction present that will produce heat. And we'll talk again about this later today, but heat is a type of energy, friction is a type of force. So you never say there's frictional energy. There's no frictional energy. It's a frictional force which produces heat energy. And if that is the case, that it's an isolated system, which means there are no outside forces acting, then the kinetic energy and the potential energy initially has to be equal to the kinetic energy and potential energy added together at some later point in time. And I'm using I and F here, but yesterday we used maybe top of the swing and bottom of the swing, or top of the ramp and bottom of the ramp. It doesn't matter what you call them. That's the law of conservation of mechanical energy. So does anybody have any questions you would like me to go over here? Go ahead, Noel. 6? Okay. All right, let's take a look at number 6. So you have a pendulum, some kind of weird looking pendulum. You have a pendulum that is in that position. It says 0.25 meters above the equilibrium position. And the question is, what is the speed of the bob as it passes through the equilibrium position, which is the lowest point? Now, do you know, and by the way, we happen to know the length of the pendulum is 1 meter. Do you know how high this is above the floor? It is 5. It does tell you?
Yeah. Yeah, on the R sheet it does.
Is it in the diagram?
Yeah.
Okay. Is the diagram, just so I know, drawn more to scale than what I have up here?
It's a little closer together.
Okay, so it's not drawn very well to scale. In other words, if you look, I'm just looking at changing my notes possibly.
It's 0.5.
Oh, it's 0.5. I thought you said 5. Okay, it's 0.5 meters. Okay. Okay, so it's maybe a little bit closer. Doesn't really matter. So this distance, and what I'm missing here is that this distance is 0.5. Is that correct?
Yeah.
Okay. So don't bother writing anything down just yet, but I'm going to tell you that a student who looks at this and is locked into the idea that gravitational potential energy is always measured relative to the floor, that student is going to do this. What they are going to say is that the mechanical energy at the top of the swing and the mechanical energy at the bottom of the swing are equal. And that's true. It's true no matter where they think gravitational potential energy is measured from. But let's look at this student who wants to measure things relative to the floor. Relative to the floor, at the top of the swing, the pendulum has mechanical energy that's in the form of potential, but because it's released from that point, or because it's the highest point, it has no kinetic energy. It's not moving at that instant. What kind of energy does it have when it reaches the bottom, which is the equilibrium position? Well, it's going to have kinetic energy because it will be moving. But if this person has said that the floor is where it has zero potential energy, then this person is going to say it also still has some gravitational potential energy there. And I want to actually show this to you because I think if you see it in action, you'll understand why we can let zero be someplace else. incidentally, the masses cancel. So maybe let's clear up that bit of business first. GH at the top equals, can we also multiply both sides by 2 here? I mean, I'm not asking if we're allowed to, I'm asking, are you okay with it? Okay. To get rid of that half, so this is where we are at. And I'm not going to put, well, I guess I will, T for top, B for bottom, B for bottom. You don't have to do that because in my mind, the left-hand side of this equation is top. So what you're going to put here is 2 times G. Now, what is the height at the top? Well, the height at the top is 0.75. Okay. So you're nodding, so you're fine with that. I'm going to leave the units out because I want to talk about the math of what's going on here. Okay. And then over here, you're going to have V at the bottom squared, and that's our goal, V at the bottom, plus 2 times G times the height at the bottom, which will be 0.5 meters, right? So when you subtract this, you're going to get 2G times 0.75 minus 2G times 0.5 equals VB squared. And I have every confidence, Noah, that you can determine V from that. I don't want you to, okay? However, a student that says instead, so this is all, everything to the left of this line is saying H is saying that H equals 0 is the floor, right? I'm going to demonstrate to you why we can put H equals 0 here. And not only why it will work, but why it will make our jobs easier. Now, how many of you, by a show of hands, understand why it's going to make our jobs easier? How many of you understand why it's going to work mathematically? Well, let's take a look. That's a different question. Here you would say the mechanical energy at the top and the mechanical energy at the bottom are equal. Because it doesn't mention friction, so we can't assume there's friction or outside forces. So this is going to be mgh at the top equals 1/2 mv squared at the bottom. Because if we're using h equals 0 at the bottom, there is no gravitational potential energy at the bottom of the swing at the equilibrium position, right? Because this is where h equals 0. So the masses cancel. I can multiply both sides by 2 and get 2gh equals v at the bottom squared. So this is going to be 2 times g times, now what is the height of the pendulum, Noah, at the top if we're saying h equals 0 at the bottom? 0.25. But these two lines, these two equations that are all on the same line are the same. I don't want to turn this into a math lesson, but I can factor 2g out of these two terms and be left with 0.75 minus 0.25. So the result is the same. It's just that by choosing h equals 0 in a strategic place allows us to get away with saying there is no potential energy at that bottom. And I should, thank you. It's 0.5, okay. So you have 0.75 minus 0.5, which is the 0.25. They're the same. So by choosing h equals 0 at a strategic position, it allows you to do a simpler calculation. Anyway, that's how you do that question. I mean, you're not going to do all of that. What you're going to do is what I have on the right-hand side of the screen. The fact that you were given the length of the pendulum and some other information is not really that relevant. You certainly don't need it. Other questions? Georgia. 10. Okay, let's look at number 10. A student is running at 3.5 meters per second and grabs a long rope that is hanging from a tree. How high can the student swing? Well, if I told you that we had a pendulum and at the bottom of the swing, the pendulum was moving in this direction at 3.5 meters per second, that's the speed at the bottom of the pendulum swing. And if I said, what will the maximum height of the pendulum be? There's a relationship between the maximum height of the pendulum relative to the bottom and the speed of the pendulum at the bottom. And we'll get back to this question in a second, but basically the mechanical energy at the top, I'm just going to be doing a lot of abbreviating here, and the mechanical energy at the bottom must be equal. Well, at the top it's going to have, I don't know that it matters. Well, I know it doesn't matter, but to a student it might. I'm going bottom to top, so I'm going to put mechanical energy at the bottom to begin with equals mechanical energy at the top afterwards. I'm just saying EI equals EF. This is 1/2 mv squared, and this is mgh. The masses cancel, and we're left with that v squared equals 2gh thing again, right? So if I told you how fast the pendulum was moving at the bottom, you could find h by taking v squared over 2g. And I rearranged for v squared because that's just what I always do. Do you see that the student is the pendulum? So if the student is running at 3.5 meters per second and grabs a hold of that rope and lifts their feet off of the ground, then they are a human pendulum. And they will have a speed at the bottom of 3.5 meters per second. So we can solve the problem now. I'm just going to finish it just in case anybody wants to see the solution. It's going to be 3.5. I'll leave the units out for this today. Equals 2 times 9.81 times h. By now you know enough that you don't go 3.5 squared divided by 2 times h, or 2 times g. You go 3.5 squared divided by 2 divided by g, or 3.5 squared divided by brackets 2 times g, right? And that's about 20, and this is not going to be very high. Well, I mean, it's a student, so I'm going to go 0.6 meters. Well, I guess the answer is here. I can just look. 0.62 meters. And there's something about this question, just the way that it's worded. How high can the student swing? Obviously, it isn't how high necessarily above the ground, but how high above where they grabbed onto it. Like if the rope is here and I grab it and I lift my feet and scrunch my feet up towards my body, what we're talking about the height being is the difference between where my feet are here and where my feet are when I get to the top, or where my hands are when I grab it compared to where my hands are at the top. Other questions? Go ahead. Number 8, okay. So a roller coaster starts at point A. If the track is frictionless, then how fast will it be moving at point C? And it starts from rest. Well, there is no difference here, Faye, between what's going on in terms of the physics ideas here compared to a pendulum. It doesn't, well, it does say it's frictionless, and let's wake up to the real world here. A roller coaster moving along a metal track, there is going to be friction. But we are here often in this class to learn how to apply physics principles to more basic situations so that later if we have friction, like today, then we at least have a start to understanding things. So if it's frictionless, which is not really ideal, meaning it doesn't actually happen in the real world, the mechanical energy at A and the mechanical energy at C are going to be the same. So what we mean is this. mgh at A plus 1/2 mv squared at A equals mgh at C plus 1/2 mv squared at C. And again, I don't really believe you need to write those subscripts all the time. I mean, the left-hand side of the equation is already labeled as A. And the right-hand side of the equation is already labeled as C. I don't know that we need those subscripts. But now we can start customizing this. Is there kinetic energy at A? Is the cart moving at A? Well, it says it starts from rest at A, right? I mean, I don't know how that works from a practical standpoint. If you're on a roller coaster, you're probably moving when you pass that point. But maybe for some reason you got slowed down and you're just reaching the top at point A, and you would normally stop there. But because you reach the top, you start accelerating down again. The bottom line is it's not moving at point A, so it has no kinetic energy. And I have a question for everybody to ponder right now. So there's no kinetic at A. Does the cart and the people in it, is there potential energy, gravitational potential energy at C?
It would depend on where you put 0.
Perfect answer. It depends. You could say yes and be correct and walk down the bumpy road to get to the answer. Or you could say no, because what you're going to do is use point C as being h equals 0. It's not the lowest point. It makes more sense with a pendulum because you can say, well, that equilibrium position of a pendulum is truly the lowest point. But it doesn't matter. Mathematically, it will work. And again, just for those of you that go on and take Physics 30, there's an important idea in atomic physics that allows us to put potential energy wherever we want, and the result is potential energy ends up being negative, because the objects are lower than where we say 0 is. Anyway, what we're going to do here, Faye, is say that h equals 0 here, and that allows us to do that. And I suspect that many of you would have just, well, I don't know, many. I suspect that some of you would have simply just dived into this, right? Because it's starting from rest. If it's not starting from rest and it's moving, then the left side would be mgh plus another half mv squared. Anyway, the masses cancel. We can multiply both sides by 2 and get 2gh equals v squared. H, Faye, is the distance horizontally between these two positions. And if this is 4 meters, boy, this is not drawn to scale well at all. If this is 4 meters to here, and it's 12 meters all the way to the top, then this distance plus the 4 has to give you the 12. In other words, it's 8 meters. So you can finish the problem now by putting in 8 meters for h. You know what g is, you know what 2 is, obviously, and then calculating v. Does that do it for you? Okay. Other questions?